Now class, picking up where we left off, we're on G. We have y to the negative 3 over y to the 4 to the second. So why don't we do this? We'll make this first, this y to the negative 3 will become 1 over y to the third all over. This will become y to the 4 times 2. Now, we'll take 1 over y to the third divided by this y to the 4 times 2 is y to the 8th. So remember, this y to the 8th is the same as y to the 8th over 1. So this will be 1 over y to the third. Division will become multiplication, and we'll take the reciprocal of the second term, or the second fraction. 1 times 1 is 1. Y to the third times y to the 8th is y to the 3 plus 8, which will give us 1 over y to the 11th. And that is our final answer for G. Now we come here to H. Now first things first, with the 14 and 21, we know both of these have 7 in common. So this will leave us a 2, and this will leave us a 3. So we will have 2 in our numerator, 3 in our denominator. Now b to the 4th will remain b to the 4th. But this b here will become 1 over b to the second power. Now c to the negative 7 be times 1 over c to the 7th. Now for our denominator, c to the negative 3 will become 1 over c to the third. Now this is a lot going on in this problem. So let's try another approach. Let's X this out because I think this would just take too long. We could still start off with simplifying, dividing 14 by 7 and 21 by 3. We could still do that. But watch this. Let's use our rules here. We know these have the same base, right? So we could bring this up to our numerator. This would be b to the 4 minus negative 2 power. Now we take our c. Same difference. It'll be c to the negative 7 minus a negative 3. Now we'll have 2. This will give us b to the 6th power. And this will give us c. We know well, I'll write that down. Negative 7 plus 3 all over 3. So this will give us 2b to the 6th. And this will give us c to the negative 4 power all over 3. Now remember what I told you all before. You could institute a shortcut here. This will give us 2b to the 6th power all over 3c to the 4th power. And we're done. That's a lot shorter than the route we were going initially. Now we go down here to objective 3. It says convert from scientific notation to decimal notation. A number is written in scientific notation if it has the form a times 10 to the n power, where n is an integer and 1 is less than or equal to the absolute value of a, which is less than 10. So it's basically telling you a can be any number that absolute value is less than 1, greater than 1, or equal to 1, or less than 10. It has to fall in between that parameter. Okay, now we have some examples here that I will give you. If I had negative 2.7 times 10 to the 6th power, that's one example. Or I could have 2.7 times 10 to the 6th power. Okay, now another example. I could have negative 1.0 times 10 to the 7th power, or negative 2.5 times 10 to the negative 7 power. Or we could have 1.0 times 10 to the 7th power, or 1.0 times 10 to the negative 7 power. Okay, now we scroll down here. Now we're given the name of the large numbers. You could look at this at your leisure. Okay, now we look here, example 6. It says write the number in standard decimal notation. Now, when they say standard decimal notation, they want us to write this number how we regularly see numbers. So we have 10 to the third power, which we know is 1,000. So that means that we move this decimal 3 places to the right. So we have 5, let me just write that out, 5.3, and we'll move that decimal 3 places to the right. So that would end up being 5,300. Okay, now you could put a comma here if you want to, you don't have to. Okay, now we have B, 8.192 times 10 to the 6th power. We know that this will end up being 1,000,000. Because if we expand this out, I didn't do it in the last problem, but I'm going to do it here. This is really 8.192 times, it'll be 1 and then 6 zeros. So this would be 1,000,000. Over here, this would have been 5.3 times, it'll be 1 and 3 zeros. Okay, so what this exponent does when it's multiplied, when it's a power of 10, all it does is tell you how many zeros you have. And we know the amount of zeros we have is how many decimal places we will move it to the right. So we have 6 zeros, so we'll move this decimal 6 places to the right. So we'll have 8,192. That would take care of 3 of the 6. And then we have 1, 2, 3 more to go. So we have to add 3 zeros. So it'll be 8,192,000 will be our final answer. Now we come here. Now this is with the positive exponents. This has a negative exponent. So we know positive and negatives are opposites of each other. So that means instead of going to the right that many places, you will go to the left that many places. So we'll need to go to the left 3 places. 1, 2, 3. So it'll be 0.0046. And that will be C. Now D, we will go to the left 5 places. So we'll go 1, 2, 3, 4, 5. So it'll be 0.000299. And that will be your final answer. Now we scroll down here. It says converting from decimal notation to scientific notation. Now it gives us the rules here. They want us to write in the form a times 10 to the n power. Determine a, the numerical factor. Move the decimal point in the given number to obtain a number greater than or equal to 1 and less than 10. Determine n, the exponent of 10 to the n. The absolute value of n is the number of places the decimal was moved. The exponent n is positive if the given number is greater than 10 and negative if the given number is between 0 and 1. Okay, let's take a look here. It says the first evidence of life on Earth dates back to, now we have this long number here, it's actually 3,600,000,000 years ago. They want us to write this in scientific notation. So my question to you is, where is the decimal? Yes, you're right. It's at the end of this number. So what we have to do here, we need to move this decimal till we only have 1 digit in front of it that is not 0. So we'll move this decimal 1, 2, 3, 4, 5, 6, 7, 8, 9 places. So we will have 3.6, and all those zeros that we had behind here, we don't have to write. So we have 3.6 times 10. We move 9 places to the left. When we're changing a decimal to scientific notation, if we move to the left, our exponent is going to be positive. So our exponent would be 9 because we moved 9 places. So it's 3.6 times 10 to the 9th power. Okay, now we come to B. It says the wavelength of violet light is about 0.00000047 meters. So now we have to move this decimal till we have one digit in front of it that is not 0. So we have 1, 2, 3, 4, 5, 6, 7 places. So we will have 4.7 times 10. Now we move this decimal to the right. Whenever we change a decimal to a a decimal to scientific notation, we have, if we move it to the right, then our answer, our exponent will be negative. So we move this 1, 2, 3, 4, 5, 6, 7 places. So it'll be 10 to the negative 7. So again, when you're changing that decimal, if you move the decimal to the left, your exponent is positive. If you move it to the right, your exponent is negative. So that takes care of A and B. Now we go down here to this section here. It says most calculators represent 7.29 times 10 to the 26 as 7.29 E 26. So this E really stands for times 10, and this number here is the exponent. Now that's what happens when you see it in your calculator on any problem. This E means times 10, and this number behind the E is the exponent. Okay, it says computation with numbers in scientific notation. Now, when we multiply these two factors together, we would take A times B, and then we would take 10, and this 10 has the same base, so we'll bring over the 10 and add our exponents. So our final answer would be whatever A times B is times 10 to the n plus m. Now, we go here, division. We have A over B, and then it'll be times. It'll be 10 to the n over 10 to the m. So what we will write down here is the decimal answer for A over B times 10 to the exponent of n minus m. Now our exponential, A times 10 to the n to the m, we'll make this A to the m, and then this will be 10 to the n to the m. Now remember, our A in every last problem, even this here when we do our A times B, we must make sure that our decimal has only one number in front of it that is not 0. And that's the same down here, and that's the same here. And we will get further explanation with our examples. So let's take a look here. We will have, this is our A and B. 2 times 3, I'll put that in parentheses, times, this would end up being our basis here. We will have 10 to the 3 plus 2. And I'll just put that in a parenthesis as well. So 2 times 3 is 6, times, this would be 10 to the 5th power. Now, typically I would say this about scientific notation. Typically you're supposed to have at least one digit behind the decimal with scientific notation. Now, what I'm going to have you all to do, I'm just going to have you all to put that. So this will actually be 6.0 times 10 to the 5th power. Now we go here to B. Now, with B, again, we would take 15 divided by 5 times, this would be 10 to the negative 4 all over 10 to the 2nd power. So this will give us 3 times, this will be 10 to the negative 4 minus 2. Now we know negative 4 minus 2 is negative 6. So this would be 3.0 times 10 to the negative 6. And we're done with that problem. Now here we would take 3 to the 4th power times 10 to the negative 2 times 4. 3 to the 4th power is 81, and this would be times 10 to the negative 8. Now remember, we must have only one digit in front of the decimal here. So we have one digit here, we have our decimal here, so we have to move this to the left one place. And that will give us 8.1 times 10 to the negative 8 and plus 1. Because remember, when we move it to the left, we add that amount of places. So it'll be